Hello, everyone, and welcome back to our KT Theory Algorithms series. Today, we're going to tackle a classic and incredibly intuitive algorithm that's widely used in knowledge tracing, naive Bayes. By the end of this video, you'll not only understand how it works, but you'll also be able to calculate it yourself. Let's get started. So, first things first, what is knowledge tracing? Simply put, it's the technology that powers those adaptive learning apps. It analyzes a student's past interactions, like which questions they got right or wrong, to model their current level of understanding or knowledge state. The ultimate goal is to predict how likely they are to succeed on the very next challenge. Today, we'll see how the naive Bayes algorithm approaches this prediction problem. To understand naive Bayes, let's use a fun analogy. Think of the teacher as a naive detective. When a student is about to attempt a new problem, the detective doesn't look at the whole picture at once. Instead, they examine each clue, like how many times the student got similar questions right before, or if they just got a question correct, completely separately. For each clue, they calculate the odds that it suggests a correct answer. Then, they multiply all these odds together for a final prediction. It's called naive because it assumes these clues don't influence each other, which is a simplification, but a very useful one. Let's formalize this with some key terms. The class is what we're trying to predict. Will the student get it right or wrong? The features are the clues we observe, like their history or speed. Now, let's look at the probabilities. Prior probability is our baseline guess before seeing any new data. Likelihood tells us, given that a student is already correct or incorrect, how likely they are to show a specific behavior. Finally, the posterior probability is the answer we're after, the total probability after combining our initial guess with all the new evidence. The image on the right illustrates how these distributions change, showing the update from prior belief to posterior certainty. Here's the magic formula, Bayes' theorem. It states that the posterior probability is the likelihood multiplied by the prior divided by the evidence. The evidence term, px, can be tricky to calculate, but since we're only comparing the probabilities of correct vs incorrect, we can ignore it for now and just focus on the numerator. And because of our naive assumption that features are independent, we can calculate the total likelihood by simply multiplying the individual likelihoods of each feature. This makes the computation extremely fast and easy. All right, let's put this into practice with our student, Xiaoming. He's about to tackle another linear equation problem. Here are his features. He's answered 3 similar questions correctly in the past. His last answer was right, and he did it quickly. Our mission is to calculate the exact probability that he gets this next question correct. To calculate, we need some pre-computed probabilities. These are usually learned from analyzing past student data. Our prior belief is that Xiaoming has a 60% chance to get it right. The table on the right shows the likelihoods. For instance, if a student gets a question right, there's a 75% chance they had 3 prior correct answers. If they get it wrong, that chance drops to 25%. We have similar numbers for the other features. Now for the math. Step 1. Calculate the numerator for the correct class. We multiply the likelihoods of all 3 features given a correct answer, and then multiply by the prior probability of being correct. Let's do the math. 0.75 times 0.85 is 0.6375, times 0.70 is 0.44625. And finally, times 0.60 gives us 0.26775. Step 2. We do the exact same for the incorrect class. 0.25 times 0.30 is 0.075, times 0.40 is 0.03, and times 0.40 gives us 0.012. Step 3 is the final step, normalization. We add the two numerators together to get a total sum of 0.27975. Then we divide the numerator for correct by this total. So 0.26775 divided by 0.27975 equals approximately 0.957. That's our answer. Based on the evidence, Xiaoming has a 95.7% chance of nailing the next question. You might be wondering, where do these 0.75s and 0.85s come from? It's actually very simple. They are learned directly from historical data by counting. The prior probability is just the overall percentage of correct answers in the past. The conditional probabilities are the percentage of times a specific feature occurred only in the cases where the answer was correct or incorrect. It's a very intuitive and data-driven approach. So, to wrap up, what makes Naive Bayes so special? It's incredibly intuitive, simple to implement, and very fast. Most importantly, it's highly interpretable. The main drawback is its naive assumption. Compared to more advanced models like BKT or deep learning-based DKT, Naive Bayes might not be the most accurate, but it offers a level of transparency and computational efficiency that is often overlooked. So, there you have it. Naive Bayes provides a clear window into how we can use probabilities to predict student performance. While more complex models exist, understanding Naive Bayes is crucial for grasping the fundamentals of knowledge tracing. Thank you for watching. Stay tuned for our next episode where we'll explore another classic model. See you then.